The Transformer 3D model extends the original Transformer architecture, designed initially for sequence data like natural language, to handle 3D data such as point clouds, 3D meshes, and voxel grids. Its primary goal is to address challenges in processing spatially and temporally structured data, especially in computer vision tasks involving 3D objects, scenes, or environments. Let's explore it in 4 parts. The Transformer 3D architecture. The main differences between the Transformer and Transformer 3D. The positional encoding mechanism function in Transformer 3D. The role of the vertex model and face model in Transformer 3D. Now let's explore how Transformer 3D architecture achieves this. The first. Key components of Transformer 3D. 1. Input representation. 3D data can come in forms like point clouds, each point defined by coordinates and features like color or intensity, or voxel grids, 3D grids representing spatial structures. To process this data, it needs encoding. This might involve positional encodings, learned or fixed, to maintain spatial relationships. 2. Self-attention mechanism. A major strength of Transformer. 3D is its self-attention, enabling the model to understand long-range dependencies with 3D position encoding. Encodings are crucial for representing 3D geometry. For instance, point clouds can use Cartesian or spherical coordinates, while voxel grids might rely on traditional grid-based encodings. 4. Transformer layers. These include layer normalization for stable training, feed-forward networks for pointwise feature transformations, and residual connections to ensure. 5. Cross-attention for multimodal data. In tasks involving multiple data types, such as combining 3D point clouds with 2D images, cross-attention aligns information across modalities, ensuring consistency. 6. Encoder-decoder structure. The encoder processes 3D input into high-level representations. The decoder is used in generative tasks, like reconstructing 3D objects, from these representations. 7. Output predictions. The final output depends on the task, ranging from class probabilities in classification tasks to 3D points or tensors in generative tasks. The second. Why Transformer 3D stands out. 1. Capturing global context. It excels in understanding relationships between distant points, crucial for tasks like object detection and segmentation. 2. Flexible input handling. Unlike CNN, it can manage variable-sized and large inputs effectively. 3. Multimodal integration. It's adept at combining 3D data with other modalities, such as text or images. 4. Data efficiency post-training. While requiring large datasets to train, it is highly efficient once trained. The third. Applications. Transformer 3D is versatile and has been successfully applied to 1. 3D shape generation and reconstruction. These models can create new 3D shapes or reconstruct incomplete ones by learning patterns from large datasets. 2. Object recognition and classification. The ability to analyze complex 3D relationships makes these models effective in identifying and classifying objects in space. 3. Animation and simulation. In graphics, Transformer 3D models can simulate realistic object movements and interactions. In summary, Transformer 3D adapts the power of the Transformer to 3D data, excelling at capturing complex relationships in space. Its flexibility makes it ideal for tasks like object recognition and reconstruction, especially in multimodal settings. Now let's explore how the Transformer and Transformer 3D architectures differ. While both share the core principles of the Transformer model, they are designed to handle different types of data and serve distinct purposes. The first. Input data type for Transformer. This model is built for sequential data like text. It processes tokens, words, or characters in a sequence where the order matters. Positional embeddings are used to help the model understand the order of these tokens. For example, in a sentence, the word order is critical to the meaning. For Transformer 3D, designed for 3D data, this model deals with spatial relationships. It processes point clouds, meshes, or other geometric structures, focusing on the arrangement of points or vertices in 3D space rather than a linear sequence. For example, in a 3D scene, the position and relationship between objects are key. The second, positional encoding. For Transformer, adds positional encoding to the token embeddings, which allows the model to understand the sequence order. This is essential since transformers process all tokens in parallel, without any inherent order. For Transformer 3D, positional encoding here is more complex, as it needs to capture spatial relationships in 3 dimensions. These encodings help the model understand the geometry and positioning of 3D points or vertices, which is crucial for tasks like object reconstruction. The third, attention mechanism. For Transformer, uses self-attention to analyze relationships between tokens in a sequence. It determines the importance of one token relative to others, which is great for tasks like translation or summarization. For Transformer 3D, adapts the attention mechanism to focus on spatial relationships in 3D space. The model learns how different points or regions interact, capturing both local and global spatial dependencies. The fourth, model architecture. For Transformer, often has an encoder-decoder structure where the encoder processes input sequences and the decoder generates output sequences. This setup works well for NLP tasks like translation. For Transformer 3D, may also use an encoder-decoder structure, but includes additional components tailored for 3D data. For example, it might handle varying densities of point clouds or adapt to the topology of a 3D mesh. In summary, while transformers focus on understanding relationships in sequential data like text, Transformer 3D extends this capability to handle 3D spatial data. It adapts the core transformer principles to process geometric and spatial relationships, opening new possibilities in computer vision, graphics, and beyond. In Transformer 3D, positional encoding plays a vital role by providing the model with crucial information about the spatial arrangement of points in 3-dimensional data. Unlike traditional transformers that handle sequences of tokens, Transformer 3D needs to understand the unique spatial relationships between points in 3D space. Let's go through how positional encoding works in this context. The first, purpose of positional encoding. In traditional transformers, positional encoding ensures the model understands the order of tokens in a sequence. In Transformer 3D, positional encoding serves a similar purpose, but for 3D data. It helps the model understand the spatial context of each point or vertex in 3-dimensional space. This is crucial for tasks like object recognition, 3D shape generation, and scene understanding, where the relative position of points significantly affects the outcome. The second, encoding methodology. 1. Mathematical formulation. Transformer 3D typically uses sine and cosine functions for positional encoding, just like traditional transformers. These periodic functions are beneficial because they allow for continuous position representations. In 3D, however, the positional encoding must represent positions in 3-dimensional space. Each point or vertex gets a unique encoding based on its spatial coordinates x, y, z. 2. Dimensionality consideration. Unlike the 1D positional encoding for sequential data in standard transformers, Transformer 3D must account for 3 dimensions. This means the positional encodings are directly linked to the coordinates of the points in 3D space, which helps the model differentiate between points based on their exact positions. The third, integration with input features. 1. Element-wise addition. Once the positional encodings are generated, they are added element-wise to the input embeddings. The input embeddings contain semantic information about each point, such as color, intensity, or other features, while the positional encoding provides spatial information. This combination ensures that each point in 3D space is uniquely represented, incorporating both its spatial position and its features. 2. Maintaining unique representations. This integration ensures that even identical points at different spatial locations have distinct representations. This is essential for the model to accurately capture how points interact and relate to each other within the 3D scene. The fourth, Enhancements over traditional methods. 1. Relative positioning. In some versions of Transformer 3D, positional encoding may focus on relative positioning rather than absolute coordinates. This allows the model to better understand how points relate to each other within a scene, which is especially useful for dynamic environments where positions might shift or change over time. This relative approach emphasizes the relationship between points rather than just their absolute locations, enabling the model to be more adaptable to changing spatial contexts. 2. Hybrid approaches. Some recent advancements combine traditional positional encoding techniques with other spatial cues from the environment. For example, depth information or other contextual features may be incorporated into the encoding process. These hybrid methods help the model interpret more complex and nuanced spatial data, improving its understanding of 3D structures in real-world applications. In summary, the positional encoding mechanism in Transformer 3D is essential for processing and understanding 3D data. By using periodic functions to encode spatial positions and combining these encodings with input features, Transformer 3D gains the ability to represent complex spatial relationships. This is critical for tasks such as object recognition, shape generation, and scene understanding, enabling the model to excel at working with 3D data. In the Transformer 3D architecture, we use two models, the vertex model and the face model, to represent and generate 3D meshes. These models are key to creating complex 3D shapes by handling the vertices and faces that make up the structure of these objects. Let's break down each model's function and how they work together. The first, vertex model. 1. Purpose. The vertex model's main job is to express a distribution over vertex sequences, which represent the individual points that define a 3D mesh. These vertices are fundamental because they help define the shape of the object. 2. How it works. The vertex model operates as a masked transformer decoder. What this means is that it generates the vertices one by one, considering the vertices it's already created. This allows the model to understand the relationships between the vertices and place each vertex in a contextually appropriate position based on the others. 3. Output. The output of this model is a sequence of vertices that define the spatial layout of the 3D object. By generating the vertices first, it establishes the foundational structure that the three-dimensional object will be built on. The second, face model. 1. Purpose. The face model builds on the work of the vertex model. Its job is to generate the faces of the mesh, which are the surfaces that connect the vertices. Faces are critical because they form the outer surface of the 3D object. 2. How it works. The face model is a pointer network-based transformer, which means it can reference and utilize the vertices created by the vertex model to form faces. It conditions the output on the previously generated vertices, determining how to connect these points to form faces. This pointer mechanism provides flexibility and efficiency in generating the mesh. 3. Output. The face model produces faces that link the vertices together, completing the mesh. This process transforms the individual points into a cohesive surface, allowing the model to generate the full 3D structure. The third, integration of vertex and face models. 1. Sequential generation. The generation process starts with the vertex model, which generates the vertices of the 3D object. Once the vertices are in place, the face model takes over and generates the faces based on the positions of these vertices. This sequential approach ensures that both models work together in harmony, creating a realistic and accurate 3D mesh. 2. Probabilistic outputs. Both models work by expressing probabilistic distributions over their outputs. This means that rather than simply generating a single configuration, each model captures the uncertainty and variability in the 3D shape. This is important because there can be many valid ways to connect points or arrange faces for any given set of vertices. The probabilistic approach lets the model explore these possibilities, leading to more flexible and adaptable shape generation. In summary, the vertex and face models in Transformer 3D work in tandem to generate complex 3D meshes. The vertex model first creates the points that define the shape, and the face model then uses these points to construct the surfaces of the 3D object. By modeling both the vertices and faces probabilistically, Transformer 3D allows for flexible, dynamic generation of 3D shapes, making it a powerful tool for various applications in computer graphics and vision.